Why is the jet pointing where it never should? On November 20th, 2025, something impossible happened. A jet of material from an interstellar object was photographed, aimed directly at the Sunday. It wasn't a glitch. It wasn't a processing artifact. It was real, captured in multiple frames from HiRISE. And the moment it appeared, it rewrote everything. Because jets don't do that. Not here. Not ever. Jets from comets, especially active ones like this, obey a kind of thermal logic. They face away from the sun, pushed by heat and gas expansion. Their direction becomes a kind of compass, telling us where the energy comes from. But this jet pointed the wrong way. It defied logic. It betrayed the thermodynamics. It stared at the sun like it didn't care. And we have no idea why. The object in question was already famous. 3I Atlas, a confirmed interstellar visitor. Its speed alone placed it beyond doubt hyperbolic, fast, never to return. But this latest development changed everything. It wasn't just its trajectory that puzzled scientists anymore. Now it was its behavior. It's a refusal to follow the rules. Because in space, jets are maps. They mark the places where energy breaks free, sublimation vents, ice pockets are rupturing into the vacuum. When light hits a volatile patch on a comet's surface, gas erupts outward, dragging dust with it. The jet forms. And because the light and therefore the heat comes from the sun, the jet always points away. Simple physics, like steam rising from a kettle. Until now, the images were subtle, not dramatic, not cinematic. Just a slight blur, a narrow stream of material emerging from the nucleus. But what made it extraordinary was the orientation, toward the light, toward the fire, not recoiling from it, but reaching into it. NASA analysts triple-checked the vectors. The stack of exposures showed no rotational smear, no convolution artifacts. The software confirmed it. The plume was real. And it faced the Sunday. Astronomers hesitated. The language of the original report was careful. Anomalous anti-tail geometry, one note read. Possible sunward jet signature, said another. But the implication was clear. Something in our understanding had snapped. There were precedents, but none like this. Some comets form anti-tails, optical illusions caused by the Earth's angle of view slicing through the dust plane. Others experience dust fallback or gravitational bending, but not this. Not a jet. Not with directionality like this. The sun is not where jets go. And then came the OH signal. Just days before, MeerKAT had detected the unmistakable 18-centimeter line, a radio whisper of water molecules breaking apart in sunlight. That alone confirmed activity. But now, the activity had shape, structure, purpose, and direction. The object wasn't silent anymore. It was performing. If this had been any ordinary comet, it might have been dismissed, a weird feature, a transient outburst. But this wasn't ordinary. This was 3I, Atlas, the third interstellar object ever discovered after Oumuamua and Borisov. And its track record was already strange. It didn't have a coma when expected. It had no visible tail for weeks. It showed non-gravitational acceleration without an obvious gas source. And now, this jet pointed where it shouldn't. Scientists offered hypotheses. One suggested a shadowed cavity facing sunward that suddenly ruptured. Another proposed a complex spin model, where vent orientation loops back under thermal torque. Some speculated on internal heat storage released asymmetrically, but none of them fit all the data. The direction still defied expectation. Because direction matters, it implies force, and force implies energy. But here, the energy came from a direction that physics doesn't predict. It was like watching smoke fall downward, or hearing thunder echo before lightning. The sequence is reversed. And with that reversal came the flood of questions. Was the object rotating in some exotic way that masked the vent's true orientation? Could solar magnetic fields redirect a charged dust stream under rare conditions? Or was this something else entirely, something not yet modeled, not yet named? Even skeptics paused. The usual voices quick to dismiss anomalies went quiet, not because they believed something unnatural was happening, but because they couldn't explain what was. Astronomy thrives on models, thermodynamic models, rotational models, albedo models, and when those break, the silence deepens. Not because we have no words, but because the words we have no longer match the sky. And so, for now, The jet remains a mystery. But what we do know is this: it was seen, it was recorded, it is measurable. And it doesn't point away from the Sunday. There's something uniquely unsettling about that. Not in a fearful way, but in a foundational way. Like standing on a beach and watching a wave pull toward the ocean, but the tide flows in reverse. Like gravity bending, not just light, but rules. Something that feels small at first, but grows in your mind. That's what 3I, Atlas, has done. It arrived quietly. No explosion, no flare, but frame by frame, it rewrote expectations. First, by its trajectory. Then, by its acceleration. Now, by its defiance. A jet pointing toward the sun is not just a direction. It's a message, a refusal, a mirror. And so we watched, and we are still watching. Not for proof of aliens, not for spectacle, but because when physics steps sideways, it's always worth following, and because this jet, this impossible jet, is still there, still aiming at the light, still asking a question we don't yet know how to answer. Can a comet change direction without visible force? That's not a casual question, it's a contradiction in motion. In the language of physics, trajectories are sacred. They are the poetry of momentum, the promise of mass obeying law. A trajectory doesn't lie, doesn't flinch, doesn't negotiate, and yet 3I, Atlas, didn't just glide. It leaned, it curved, it seemed, for a moment, to decide. When it first entered our awareness, 3I, Atlas followed a clean hyperbolic arc expected for something not of this solar system. No previous ties, no future return. It was outbound before it even arrived, but as telescopes caught more of it, something broke the script. Its path, though subtle, began to stray, not wildly but consistently, defying what gravity alone could explain. This wasn't noise. The rotation curve plotted from photometric light variations showed not just spin, but precession. The object wasn't tumbling randomly. It was pivoting, as if a hidden hand nudged it mid-flight. In every natural model, such behavior demands a reactive force. That usually means outgassing, a jet or plume erupting unevenly from a sunlit surface, creating thrust. But here is the puzzle. The direction of the deviation didn't match any observed jet. In fact, it didn't match any visible force at all. The infamous plume captured in NASA's latest HiRISE composite pointed toward the Sunday. That should produce reverse thrust, not lateral. And yet, the turn was there. There are rules in comet science. Conservation of momentum is one of them. You don't accelerate without a push. You don't pivot without torque. 3I, Atlas, was accelerating. It was pivoting. And every force we could see was either insufficient or in the wrong direction. Was this an illusion? Could the models be wrong? Perhaps. Some argued it was observational error, an issue of viewing angle, an artifact of data stacking, or even a misread of time dilation near perihelion. But the signal held across instruments and time zones, from the ground and from orbit. The change was consistent. Others proposed something more complex. Delayed sublimation, maybe 3I. Atlas carried internal pockets of CO2 or HCN, and when heated from the inside, these vented not from the sunward side, but at odd angles through surface fractures. It's plausible, but still, why that specific curve? Why that timing? There's a diagram that circulated quietly in research. Slack channels, a map of observed versus predicted positions over 10 days. The residuals formed a gentle arc, not random noise, but a smooth deviation. It wasn't a zigzag. It wasn't chaotic. It was almost choreographed. This word choreographed troubles scientists. It implies intent where none should be. But the data doesn't lie. If 3I, Atlas, was spinning in a particular way, with specific surface geometry, it might create net motion from asymmetric outgassing, but then the vent geometry would have to be near perfect, aligned just right to redirect motion over weeks. And that brings us to a deeper question. How much precision is too much for nature? This isn't a suggestion of artificiality, not yet, but it is a suggestion of constraint. When things behave in ways that require finely tuned parameters, our models begin to itch. We call them edge cases. We blame incomplete data. But what if we're seeing exactly what's there, and it's our assumptions that are incomplete? Even the timeline adds tension. The pivot began just before the OH-18cm signal was detected by MeerKAT, indicating active water chemistry. Could that activity be responsible for the deviation? Possibly. But water jets tend to produce chaotic motion, not smooth arcs. Unless, of course, the jets were modulated, pulsed, even. But comets don't pulse. Not with regularity, not without feedback. And 3I, Atlas seemed to respond to sunlight like a sail, not just with heat, but with intent. When it turned, it exposed new surfaces. When it exposed new surfaces, it changed brightness. When it changed brightness, it adjusted its motion again. And yet, it never broke apart. All of this happened in a body roughly 150 meters across. That's small. Smaller than a football field. For context, that's about a tenth the size of a typical comet nucleus. And yet, it resisted tidal forces near perihelion. It held together. It turned without cracking. It moved without disintegrating. No visible fragmentation. No secondary trails. Just motion. One paper from early November suggested rotational deceleration, which would imply loss of angular momentum possibly from mass ejection. But no mass was seen leaving. Only a thin, faint plume pointing inward. And that brings us back to the impossible. If the jet points toward the sun and the body moves away from the expected path, then the force vector doesn't match the outcome, which leaves only one conclusion. Either the jet we see is not the source of the thrust, or there is another force we haven't yet detected. Some observers speculate about delayed force mechanisms, jets that fire, then affect motion minutes or hours later due to spin, lag, or internal diffusion. Others wonder if there's an internal gyroscopic effect, mass moving within the object that shifts its center of mass gradually. But that implies internal complexity. A comet, by definition, is a dirty snowball. It's not supposed to be a machine. And yet, if 3I, Atlas, had baffles chambers, compartments, or variable vents, it could, in theory, act like a self-modulating object, one that adjusts, one that responds, one that turns. And so we are left with a dilemma, not of belief, but of a model. Do we stretch our physics to match this curve? Or do we stretch the curve to protect our physics? Because the object turned. We all saw it. The instruments agree. The motion was real, and nothing we've seen explains it fully. These images weren't supposed to exist, at least not like this. In early November, when the NASA HiRISE team scheduled their snapshot of 3I, Atlas, the expectation was modest, a dim smear, maybe a central condensation, but likely nothing at all. The object was already past perihelion, already leaving the inner system. Detection itself would be a victory, a data point, a pixel of light. But what came back wasn't just data, it was a rupture in the pattern. Because one of the jets in the image, if it truly is a jet, appears to point toward the Sunday pause. That sentence shouldn't make sense. Jets from comets don't behave like that. Outgassing follows sunlight. The side facing the sun is warm. It heats the volatile material inside the object. That material turns to gas. That gas escapes. And the direction of that escape is by definition away from the Sunday. That's why comet tails stream backward. That's why anti-tails, when they appear, are rare, geometric tricks of alignment. They don't physically point forward. They only appear to. Except, this one might be different. Let's go slowly, frame by frame, image by image. Through layers of calibration, timestamps, and context, the HiRISE camera, mounted on the Mars Reconnaissance Orbiter, captured a tightly framed segment of the sky as 3I, Atlas, moved across it. It wasn't tracking the object, it was doing a fixed-point stare, waiting for the object to pass through. That method creates streaks. Objects in motion blur into lines. That's how they spotted it. A faint, linear mark, consistent with expected motion, brightness, and timing. But here's where things diverge. Across several exposures, the streak is not uniform. In two of them, a fan-like extension arcs outward from the main line. This fan doesn't follow the trailing geometry of expected outgassing. It bisects the line, and it bisects it in the direction of solar incidence. In other words, it points toward the Sunday. What's more, when stacked with solar position data and overlaid with ephemerides, the orientation of this fan holds steady relative to the solar vector. That's not noise. That's not an artifact. That's geometry. Could it be a processing error? That's always the first question. So let's examine the image stack. When you align the raw HiRISE captures with SOHO imagery, taken in overlapping timeframes from a radically different vantage point, the shape appears again. Not as clearly, not as finely, but present. A solar-aligned extrusion that follows 3I, Atlas, through several hours of motion. And it isn't fixed in camera space, it's fixed in the sky. That's crucial, because it suggests the phenomenon is not a lens flare, not a stacking ghost, not a motion blur quirk. It moves with the object. It behaves like something real. Still, caution remains. Brightness curves show an asymmetry near the midsection of the streak, a hump in the light curve that correlates with the appearance of the jet. This is important because it suggests not just shape, but energy, a release, a venting, a momentary increase in reflected or emitted light, which could imply, and this is still a hypothesis, active behavior during the imaging window. That brings us to the next image. SOHO's LASCO C3 captured a wide-angle perspective of the inner system. In most frames, 3I, Atlas, is a dim dot, indistinguishable from background stars. But during one specific moment when HiRISE saw the fan, SOHO sees a flare. Not huge, not dramatic, but measurable. The dot becomes elongated, directionally elongated, and again, the elongation points sunward. We now have three signals: a fan-shaped feature in HiRISE that intersects the object track toward the Sunday, a brightness increase in the HiRISE light curve at that exact position, a directional flare in SOHO imagery, aligned in the same direction. That triangulation doesn't confirm, but it strongly suggests the presence of an anomalous jet. And now the question shifts. If it's real, why would a jet fire toward the sun? Outgassing physics says that's thermodynamically inefficient. It would require material to be expelled against the pressure gradient. It would require internal mechanisms, vents, fractures, or spin-locked apertures to be oriented contrary to expectations. Unless the outgassing isn't driven solely by sunlight. This is where models start to crack. Let's consider rotation. If 3I, Atlas is spinning, and the vent is positioned near a rotational pole that happens to be aligned sunward, then the jet could plausibly trace a path that leads toward the sun, not because it seeks the sun, but because of mechanical orientation. Think of a garden sprinkler angled just wrong. The water goes where it shouldn't, not because it wants to, but because that's where the nozzle aims. But that still doesn't resolve the energy puzzle. For a jet to sustain visibility across both HiRISE and SOHO, it has to be active, not residual. It must have a source of energy sufficient to drive the escape velocity of gas and dust. And it must do so while already beyond perihelion, when solar input is declining. So what fuels it? Some theories suggest crystallization of amorphous ice, a phase change that can release latent energy deep within the body. Others point to volatile pockets, CO or CO2, rich regions that can vent explosively when breached. But neither easily explains a consistent sunward orientation. Both would produce isotropic or surface-aligned plumes, not this strange, forward-facing spike, which raises the last possibility: geometry. Specifically, observer geometry. Could it be that what we interpret as a sunward jet is actually a perspective effect, a tail or sheet of dust aligned obliquely in 3D space, but appearing head-on from our angle? It's possible, but unlikely, because the angle between SOHO and HiRISE is wide, not enough to create parallax confusion. Both saw the extrusion, both noted alignment. That alignment isn't a coincidence. It's a clue. In the end, we're left with what all great images give us. Not answers, but better questions. What process could drive sustained outgassing against the solar vector? What geometry would be required for that jet to remain visible across multiple observers? What does this say about the internal structure of 3I? Atlas, its vents, its spin, its composition? And what does it mean when observation trumps simulation? Because the simulation said no, the models said impossible, the physics said unthinkable. But the images? The images say, look again. Sun-facing jets contradict all comet models. Everything we know about comets begins with light and the heat that light carries. That's where the jets come from. When sunlight strikes volatile materials on a comet's surface, it heats them. Those ices water, CO2, sometimes carbon monoxide sublimate, turning directly from solid into gas, and that gas erupts, not randomly, but always away from the Sunday. The logic is simple. The sun is the energy source, so the jets always point back like steam from a kettle held to the flame. But now imagine this. 3I, Atlas, the interstellar object, is seen with a plume facing the Sunday, not trailing it, not perpendicular to its motion, not diffused around a coma like a fog, but pointed toward the Sunday. That's not how sublimation works. That's not how physics works. And yet, that's what the image shows. In every model we've ever built for cometary behavior, non-gravitational acceleration comes from outgassing specifically from jets that form on the sun-facing side, then push the nucleus away from the Sunday. The force is reactive, like a rocket. The gas escapes in one direction, and the comet drifts slightly the other way. But this model only works if the vent orientation, spin rate, and thermal input follow certain constraints. 3I, Atlas appears to break all of them. Let's look at sublimation again. The heat absorption from sunlight is uneven. The day side warms, the night side cools. As the object rotates, new areas are exposed. That heating-cooling cycle is what defines jet behavior. You get spirals, you get arcs, you get fragmented structures that sometimes behave erratically but never directly into the sunlight. Why? Because heat can't preemptively act. It needs contact. The gas can't erupt before the surface warms. There's no reverse combustion in space. That would imply internal heat moving against the energy gradient, outflowing toward a hotter environment. So, how do we explain this sun-facing plume? Some proposed an optical illusion. Perhaps it's not a jet at all, but a forward-scattered dust reflection, or an artifact from image stacking. But that argument collapses when you consider the consistency. Multiple frames, multiple instruments, different telescopes and wavelengths, each confirming the same geometry. Others speculate maybe the nucleus has vented gas from a shadowed region facing forward due to internal stress. But again, why would an internal stress pattern release material directly sunward? Another possibility, the comet has flipped. That is, its rotation axis is aligned in such a way that a vent now happens to face the sun and vent material in that direction. But even in that case, the result should not look like a narrow, collimated jet unless the structure of the outgassing is extremely focused, like a nozzle. Nature doesn't make such nozzles often, and certainly not on tumbling interstellar rocks. There's a deeper tension here, non-gravitational acceleration. That's the fingerprint. Normally, when we see unexpected changes in trajectory, tiny drifts that deviate from gravity-only models, we blame jets, and we have equations for that, the Marsden formulae. The comet activity models, they allow us to approximate force vectors based on jet timing, strength, and solar flux. But 3I, Atlas doesn't just show signs of acceleration, it shows signs of wrong direction acceleration. If the jet is pushing toward the sun, that implies the object should be slowing down, losing orbital energy, spiraling inward. But that's not what we observe. Its trajectory remains outbound, interstellar, hyperbolic, and dynamically consistent with a visitor that's leaving. This is where the models crack. What if the gas isn't coming from sunlight at all? Could it be internal heat? Radiogenic decay? That's possible in large bodies, asteroids, moons, but not for a 200-300 meter object like this. It would have long since cooled. No internal fire remains, no residual warmth to drive pressure outward. The only known mechanism left would be active vent engineering, a mechanism designed not just to release pressure, but to control direction. That's not something we expect from nature. That's something we build. Now we step carefully. We're not claiming aliens, we're not even claiming intent. But when a jet appears to behave counter to every known mechanism, we are forced to revisit assumptions. Maybe we missed something. Maybe there's a new kind of sublimation we haven't modeled. Maybe the object's surface contains materials that react differently to solar flux. Or perhaps the coma is hiding geometry we can't resolve with current instruments. But even those concessions struggle to explain a jet that appears to fire into the sun without disintegrating and while maintaining its trajectory. So we return to the photos, and we remember. The image shows the result, but not the cause. We see a bright, narrow structure. It aligns against the expected motion. It remains visible across frames. It exhibits properties of a real feature, not an artifact. That means either the jet is real, or we don't understand what a jet is anymore. And if we don't understand that, then everything else, rotation models, trajectory drift, energy budget, must be reconsidered. This is why physics doesn't allow it, because physics, at its core, depends on symmetry and conservation. Heat flows from hot to cold, gas expands into a vacuum, motion follows force, and yet here, something moves, without obeying any of those rules. So we end with a puzzle. If this jet is real, and it faces the sun, then either it's not a jet, or it's not from a comet. What if we've misunderstood the tail itself? For centuries, a comet's tail was seen as a signature, its plume of dust and gas unfurling away from the sun, pushed outward by solar radiation and wind. It was one of the few visual constants in a universe full of unpredictability. The logic was clear. The sun heats the icy nucleus, gas and dust sublimate, and pressure sends the material outward, always away from the Sunday always. But then came 3I, Atlas. On several frames, clear, sourced, time-stamped, we see something that shouldn't be there, a luminous extension pointing toward the Sunday. Some called it a jet, others called it a tail. Some, desperate to reconcile what they were seeing with what they thought they knew, called it an illusion. But illusions demand structure, and in the world of comets, illusions often come down to angle specifically, the angle between Earth, the object's orbital plane, and the stream of particles left behind. This is where the concept of an anti-tail enters. In theory, an anti-tail is not a real tail, it's a trick of geometry. When Earth's position crosses the plane of the comet's orbit, we may temporarily see the trail of dust particles normally left behind in a flat, expanding sheet, as if it were pointing toward the Sunday. Not because the particles are defying physics, but because our line of sight intersects the orbital dust plane at a glancing angle. Imagine a flat disk of chalk dust suspended in space. If you look from above, the dust spreads out like a halo, but if you lower your perspective and look edge on, that disk sharpens into a thin line. Depending on where you stand, that line may appear to point in any direction, perhaps even back toward the source. But here is where 3I, Atlas, breaks that explanation. Anti-tails are rare and short-lived. They require precise alignment. Earth must pass almost exactly through the comet's orbital plane, and the tail itself, made of heavy dust particles, must be broad, slow, and well-behaved. 3I, Atlas, however, isn't well-behaved. Its trajectory is hyperbolic, its plane is steeply inclined, and most critically, it's not shedding broad, slow dust. It's emitting narrow, bright, dynamic jets. If this is an anti-tail, it's the strangest ever recorded. Researchers tried to model it. They took the known orbit of 3I, Atlas, and Earth's position on the observation dates. They simulated the backscatter geometry to see if an anti-tail could appear sunward. Some results were promising, others impossible. The biggest problem? The feature remained visible across multiple observation windows, spanning weeks, longer than a typical anti-tail illusion should persist. This suggests either a stable physical structure or repeated, sustained emission in a fixed direction. That's not how anti-tails work. Even in famous cases, like Comet Arend-Roland in 1957 or Comet Pan-STARRS in 2013, anti-tails flickered into view for brief periods. They were often faint, short, and explainable via plane-crossing geometry. But this was none of those things. Some pointed to dust alignment models. Maybe the particles were larger, slower to disperse. Maybe there was a secondary event, an early burst of dust that created a trail weeks earlier, and Earth's alignment revealed it later. It's possible. But even that doesn't solve everything, because this jet or tail, or anti-tail, is too sharp. Anti-tails tend to blur at the edges. The farther the dust spreads, the more it diffuses. But the structure in these images was narrow. It resembled a spike. Some compared it to an exhaust tight, defined, directional. And it didn't fade the way dust normally fades. Could it be gas, not dust? Possibly. But gas would disperse too fast to leave a coherent structure over days. And if it's gas, it shouldn't be forming an anti-tail at all, because anti-tails are dust phenomena. So if it's dust, it's too sharp. If it's gas, it's too stable. We are left in a paradox. If it's an anti-tail, it's unlike any previously documented. If it's a jet, then it breaks known physics by aiming toward the Sunday. If it's both, then it implies a hybrid phenomenon, a dust structure aligned like a jet, but shaped by orbital geometry. That leads us to ask a deeper question. Are we sure we're seeing a single phenomenon? Maybe the mistake is trying to categorize this as just a tail, or just a jet, or just an illusion. Maybe we're seeing a composite. A jet partially shaped by sunlight and sublimation, overlaid with a dust trail angled just right to appear sunward from Earth. Or maybe we're seeing something else entirely, a directional burst from the object's surface, aligned toward its orbital path, timed with a shift in spin orientation. A low-mass, high-albedo plume is visible not because it exists long, but because it reflects just enough. A spike of memory, not material. A light echo of what once was. Whatever it is, it's made the visual language of comets uncertain again. No longer can we look at a tail and assume its direction tells us anything about its motion. No longer can we trust that jet equals away from the Sunday. And maybe that's the most important part. Because if we can't even trust the direction of a comet's light, how can we trust our eyes? The anti-tail of 3I, Atlas, has become a mirror. It reflects our assumptions, our biases, our hunger for clean models. It reminds us that some illusions aren't optical, they're conceptual. That the most persistent illusions are the ones we think we've already solved. And in that light sunward, paradoxical, undeniable, it forces us to look again. Section 5 complete. Awaiting your okay to proceed to the next section. What we heard changed everything we saw. At first, it was only a light, a smudge across the frame, a thin beam stretching oddly toward the Sunday. We questioned the image, the optics, the dust, but something else had already begun whispering through the dark long before those photos made headlines. It wasn't visual, it wasn't dramatic, it was quiet, predictable, a frequency long known to astronomers, but often overlooked by those who look only for light. 18 centimeters. That's the wavelength. A slice of the electromagnetic spectrum reserved for one specific signature, the hydroxyl radical, OH. When ultraviolet light strikes water molecules in space, particularly those ejected from comets, it splits them apart. One of the fragments is OH. And this fragment, this tiny molecule adrift in the solar wind, sings, not in any audible sense, but in a frequency so stable, so universal, that even a telescope half a planet away can pick it up. And one did. MeerKAT, the South African radio observatory, known for its precision and low-noise environment, tuned into the void and heard something it wasn't expecting. A spike. A clean, unmistakable emission line at exactly 18 centimeters. That alone would have been intriguing. But it wasn't just the presence of the OH line, it was the strength. The signal was well above background, it was coherent, and most importantly, it was located exactly where 3I, Atlas, should have been. That detection rewrote the frame. Until then, there had been speculation. Could the jet be from embedded CO2 or some other exotic volatiles? Could it be a non-volatile fragmentation event, sending dust outward in a slow, symmetrical halo? Some suggested it was a mirage, the byproduct of stacking errors or directional bias in image registration. But radio doesn't lie. Unlike light, which can scatter, reflect, distort, and mislead depending on angle and medium, radio emissions, especially at this frequency, cut through noise like a tuning fork in a silent room. It wasn't just confirmation of water, it was confirmation of activity. The object wasn't inert. It wasn't dead rock. It was outgassing, releasing volatile compounds in a directional stream, likely through a jet. And that changed everything. If a water-based jet was active, the source had to be sunlit, and yet the jet pointed toward the Sunday. This is where the tension thickened. Standard models of cometary behavior suggest that jets form on the night side or the subsolar terminator places where the surface can heat gradually and force sublimation through weak crusts or fractures. But this was different. The OH signal implied a daytime source, a sun-facing outgassing event. Precisely the configuration that traditional sublimation theory says shouldn't happen. Unless something else was going on, perhaps the surface of 3I, Atlas, was unusually smooth, or perhaps its spin axis was aligned such that we were seeing a polar jet. That might explain the persistence of a single, stable direction. But if so, why the OH emission was so strong, especially from a body supposedly depleted after perihelion, remained a paradox. And yet, the signal didn't disappear. It persisted over multiple nights, multiple passes. Other radio observatories began to tune in quietly, cautiously. Confirmation trickled in. The signature wasn't a fluke. The jet was real. The water chemistry was real. The alignment? Still impossible. There's something poetic about a radio telescope catching what our eyes dismissed. The public narrative was still focused on the image, the jet pointing the wrong way, but scientists knew the deeper story was humming in the background. The OH signal wasn't just confirmation, it was implication. It meant the object was thermally alive. It meant internal heat or structural shifts might still be shaping its motion. And more disturbingly, it meant that all of our assumptions about jet geometry needed revisiting. Could there be a mechanism by which sun-facing surfaces release gas more efficiently? Perhaps microfractures that reopen at peak stress? Could outgassing itself be causing temporary reorientation of surface plates, effectively rotating the jet aperture mid-orbit? These were no longer fringe theories. They were the only theories left, and all because of a radio line. Sometimes, in astronomy, the things we hear matter more than the things we see, especially when both are saying the same thing just in different languages. Light gave us confusion. Radio gave us coherence. In that way, the OH detection became a pivot in the story. Not a climax, but a hinge, a confirmation that pulled the entire narrative away from speculation and towards structured uncertainty. We still didn't know why the jet pointed toward the Sunday, but now we knew it was real, active, molecularly consistent with known cometary chemistry, and yet geometrically inconsistent with known physics. That duality became the core of the mystery. And for those watching carefully, it was a signal not just from 3I, Atlas, but from the limits of our own understanding. The object was still far from Earth, still weeks from its closest pass, but in the long arc of its approach, it had already done something most celestial visitors never do. It spoke. And when we listened, the story shifted not just in direction, but in depth. If the jet is real, where is the hole? We've all seen it now, frame after frame of a structured plume, extending not away from the sun, but toward it. But if we accept that this isn't a camera glitch or an artifact of image stacking, then we're left with one haunting question. Where is the source? A real jet must come from somewhere. A vent, a fissure, a crack in the nucleus. And yet, despite weeks of analysis, no such point has been clearly identified. No localized brightness, no hotspot rotation, just a shadowed geometry that keeps refusing to confess. Let's start with what we do know. 3I. Atlas is rotating. Its light curve isn't flat, it pulses, suggesting a complex, possibly tumbling motion. But that variability alone doesn't explain the directionality of the jet. In classical comet physics, the vent where material escapes must align with sunlight. Heat penetrates the surface, sublimates ice beneath, and pressure builds until a jet erupts. Simple thermodynamics. But a jet aimed toward the sun implies a vent on the sunward face, something that should be overwhelmingly illuminated, not hidden. If the jet were there, we'd expect brightness, flare, and rapid evolution of the coma. We'd expect violent variability. But instead, we see relative steadiness, a gently pulsing object whose jet points where physics says it shouldn't. This paradox has led researchers to look for alternate vent geometries. Could the object's spin be exposing hidden regions? Maybe the nucleus is oddly shaped like a sheet or pancake that wobbles in and out of direct sunlight, venting in pulses. Or perhaps the spin axis is tilted just right to send a stream not outward, but along the solar vector, even as the surface receives only glancing thermal input. Avi Loeb's team suggests a more radical model. What if the jet isn't responding to sunlight at all? What if it's pressure-driven by internal reservoirs, possibly triggered by tidal flexing near perihelion? That would explain the jet's persistence in the wrong direction and why its brightness doesn't correlate cleanly with solar angle. But there's another problem. If you map the direction of the plume across time between SOHO's earliest shots and HiRISE's sharpest frames, it appears to track the orbital motion, not the Sunday. In fact, the jet stays aligned roughly with the comet's path, not its illumination. That would be consistent with a vent placed opposite to the orbital motion blasting material backwards as the object races forward, a sort of aerodynamic braking thrust. But again, that doesn't explain the sunward direction unless the geometry is extremely skewed like a nozzle aimed along a bizarre axis, fixed in rotation, and yet no precision. No wobble in the jet's orientation, just persistence. Another theory arises. Maybe the jet is tied to a specific latitude or longitude on the nucleus. If so, and if the spin is locked or harmonically synchronized with the orbital motion, then the jet would always face a particular direction, even if that direction contradicts sunlight. This would imply an engineered stability, something we don't expect in random cosmic debris. A rotation locked to a trajectory? It happens, but rarely. We see it in satellites, occasionally in captured asteroids. But in a presumed interstellar object, that's where speculation deepens. The difficulty in locating the vent may not be observational error, it might be a symptom of something else entirely. The plume appears structured, consistent, and narrow, not a cone, not a wide fan, and not diffused like we see with CO2 outgassing from icy surfaces. That raises the possibility that it isn't even a traditional jet at all, but a guided release, a channeled emission. In recent modelling by South African astronomers working with MeerKAT data, they noted that OH emissions associated with water breakdown were offset from the main jet's visual line. This suggests a layered plume, one component seen in radio, another in light. One hot, one cooler. That kind of separation isn't typical. It implies a structure in the ejection process. Then comes the axis question. If 3I, Atlas, is spinning along a short axis, the material should spiral, not travel in a straight, persistent line. Yet, in multiple observations, the plume shows minimal curl. That requires either 1. A very slow rotation rate, 2. A vent located along the spin axis, a pole, so it doesn't rotate out of view, 3. Or, again, a form of stabilization. The HiRISE team attempted a rudimentary axis model using differential photometry tracking shadows and reflection across the object's surface, but even their estimates vary wildly. Some solutions suggest a low inclination spin, others a high angle tumble. None explains the lack of plume deviation, and we return to the central dilemma. If the plume is real, structured and persistent, why can't we see the hole it's coming from? The images don't show thermal hotspots, no clear ejection flash, no surface alteration across orbits. The object remains dark, muted, mysterious. What's worse is that the plume seems to interact with light in non-obvious ways. Observers using polarized filters at Cerro Tololo report brightness shifts along the jet axis that suggest collimation, as if the particles are aligned, not scattered. That points to magnetic confinement or electrostatic ordering, neither of which appears in natural comets to this degree. Unless this isn't natural, but before we fall off that ledge, let's admit, the hole might simply be on the far side. The plume might be curving, not straight. The imaging might be stacking artifacts. All possible. And yet the question doesn't go away. If a jet is pointing toward the sun and keeps pointing toward the sun, then either our models are wrong or the source isn't where we expect. So, we keep looking. Through thermal frames, light curves, spin simulations, and radio maps. Not for certainty, but for consistency. If there's a vent, it's hiding. If there's no vent, then the plume isn't what we think it is. And if the plume isn't what we think it is, maybe the object isn't either. No model can make its point that way. The math doesn't line up, not the way it's supposed to, and not the way it must if this were just another comet. You can plug in the standard inputs: mass, albedo, orbital velocity, solar distance, use the same algorithms we've trusted for decades. But something breaks again and again when you try to make it match the real sky. Every time you simulate the plume seen in the NASA HiRISE images, the trajectory veers off. The output diverges from the visual input. The jet, the anti-tail, the shift, it refuses to obey the models. Why? Because no model, no physical system based on solar sublimation and known spin geometry can produce a sustained jet pointing toward the sunday. Let's start with what should happen. In standard comet physics, solar heating causes volatile ices, typically water, CO2, CO to sublimate as the nucleus approaches the sunday. This outgassing escapes through vents on the sunlit side. The momentum from this gas escape pushes the comet ever so slightly in the opposite direction, creating the familiar dust tail pointing away from the sunday. This is what creates non-gravitational acceleration. It's simple, elegant, and consistent with decades of observation until now. 3I. Atlas doesn't play by those rules. The image shows a jet pointing almost sunward, not perfectly aligned, but unmistakably angled against the solar vector. And when scientists tried to simulate the conditions that could result in this configuration, none of the parameters worked. No orientation of spin, no combination of vent location and surface activity, no plausible albedo pattern. Even if you tweak the model to allow for extreme asymmetry, say, a vent placed on the far terminator edge and angled sharply, the resulting acceleration vector still doesn't align with the observed motion or the projected plume geometry. It gets worse. When attempting to align the observed non-gravitational acceleration vector with the presumed source of the plume, modelers encountered a mismatch between the direction of energy input, sunlight, and the direction of momentum output, plume. This violates conservation expectations unless 1. The comet's body is redirecting force in an unknown way, 2. There's another source of energy not accounted for, or 3. The jet isn't a jet at all. And yet, we have the OH 18 cm signal confirming water breakdown. We have the image stack showing a sustained release of material. We have motion. So, what isn't working? The first suspect, spin modeling. If 3I, Atlas, were spinning in a chaotic, tumbling state, that might explain inconsistent venting. But the photometric light curves suggest a relatively stable rotation, not chaotic enough to justify random directionality. The second suspect, vent location. Maybe the jet comes from the shadowed side due to thermal inertia. That's been modeled. But it still doesn't create a persistent plume against the solar vector. Thermal lag can delay outgassing, but not reverse geometry. The third, reflectivity error. If we're misinterpreting the direction of the plume due to brightness artifacts, then the jet might not point where we think. But HiRISE and SOHO processed images across multiple filters. The tail remains consistent. So theorists turned to advanced simulations. They included variable jet strength, rotating vents, tidal stress, surface fragmentation. But still, no model reproduced what the real sky showed. The anti-tail remained unexplained. The direction defied the math, and perhaps most notably, energy mismatch became the core contradiction. Outgassing requires energy. The plume seen on 3I, Atlas, would require solar input sufficient to sublimate water ice into gas, with enough momentum to create that arc. But that amount of energy should have shifted the comet's motion visibly more than observed. Instead, what we see is high-efficiency directional venting, without matching recoil. A phantom jet, in modeling terms visible, but not accounting for enough motion. That's the paradox. Imagine striking a match in a vacuum. You see flame, but you feel no heat. You see thrust, but there's no force vector on the object. That's what the simulations are telling us. The force appears without proportionate consequence. The glow appears without a required cause. And even when you strip down to the most basic Newtonian mechanics, remove all thermodynamics and chemistry, and just apply conservation of momentum to a body, accelerating against the vector of sunlight, there's a residual mismatch. This is where the simulations begin to fail, not just physically, but conceptually, because we can no longer answer the question, what is the source of directional momentum here? And if the models can't answer that, then something is missing. We may be using the wrong physics. We may have failed to account for exotic material properties, superconductive ices, phase change reflectors, magnetic interactions. This may be a composite object, with internal structure designed to direct jets in non-conventional ways. But unless we allow for those unorthodox assumptions, the models fail. They fail in shape, they fail in spin, they fail in light, and most of all, they fail in logic. This isn't a case of, we need better telescopes, it's a case of, we need better questions. Because at the center of this plume, this sunward arc that no model can explain, is a problem we don't yet know how to ask properly. And maybe that's where it begins. It shouts through light but whispers through silence. If it hadn't been for the plume, we wouldn't have noticed anything unusual. The images caught our eye, first flashes of brilliance in places they shouldn't be. Jets dancing sunward when every known rule said they shouldn't exist. Yet for all its flare and light, 3I, Atlas, made no sound. Not the kind we could measure. Not the kind of space that usually gives us when something moves that violently. Because typically, when a comet becomes this active, when gases erupt, when solids fragment, when a nucleus turns chaotic, it creates noise. Not audible, of course, but electromagnetic. Bursts, echoes, fluctuations across the spectrum, and sometimes surprises. Yet none came. Even after telescopes around the world were trained on it, no high-energy spike emerged. No microwave outburst, no gamma flicker, no unexplainable pulse from within the static. The data was, in a word, silent. It wasn't just an absence of alien signals, it was an absence of everything. There was the OH line, the 18 centimeters radio emission caused by water disintegration. That was real. That was loud, in its own way. MeerKAT caught it. Others confirmed it. But it was a chemical whisper, not a statement, not a message. Beyond that, the skies were still, and that stillness, ironically, speaks volumes. It suggests that whatever is happening on the surface of 3I, Atlas, is governed by forces that don't leave electromagnetic fingerprints. It erupts, but doesn't scream. It moves, but doesn't echo. It pushes against the sun, but the sun doesn't seem to push back. How can something be that alive in the light, and that dead in the noise? Astronomers listening with the Green Bank telescope heard nothing new. FAST in China scanned past its coordinates and noted no irregularities. Even arrays designed to pick up the hum of the cosmos itself, the quiet resonance of space-time, heard nothing out of place. The same frequencies present before the plume remained untouched after. This, in itself, became a mystery. Because something with that much visible activity, with a jet strong enough to change trajectory, should create a disturbance. The kind you can chart. The kind that spills across multiple wavelengths. And yet, the data was cleaner than expected. Too clean. One researcher called it an anti-event, where activity occurs without consequence. A jet appears, but doesn't disturb its environment. An object rotates, but leaves no wake. A trajectory shifts, but the sky remains unbothered. Some hoped we'd find something hidden, an encrypted frequency, an unnatural pattern, a spectral anomaly. Not because they believed in extraterrestrial contact, but because silence leaves fewer clues than chaos. If it had screamed, we'd at least have somewhere to begin. Instead, we're left with a paradox. A comet with an impossible jet, moving in defiance of models, photographed doing something it shouldn't, and producing none of the noise that should accompany it. It's as if 3I, Atlas, is designed to be seen, but not heard. A performer on a cosmic stage, bright under the spotlight, but deaf to applause or inquiry. Some call this elegance, a natural mechanism so finely tuned that it wastes no energy. Others suspect masking, perhaps the same mechanism producing the jet also shields the signals, diffusing energy along narrow bands we're not yet listening to. But that too is conjecture. The data doesn't lie, it just remains incomplete. We looked at the angle of the plume, measured its brightness, and mapped the changes over time. We layered Hubble imagery over SOHO frames, timed them to the OH signal detection window, and searched for flares or secondary signatures. We aligned the venting pattern with Earth's line of sight, hoping that maybe the silence was an illusion, just poor geometry. Still, nothing. Not even a whisper on low frequencies. Not even a blink on higher bands. Just outgassing. Just ice and light. It's tempting to think that silence means absence, that no radio burst equals no intelligence, that no pattern means randomness. But the history of observation tells us otherwise. Jupiter doesn't speak when it consumes a comet, but its scars remain for months. Pulsars don't glow visibly, but their radio cadence becomes the heartbeat of galaxies. Silence, in space, is never neutral. It can mean dormant, it can mean hidden, it can mean waiting, and sometimes it can mean you're watching something built not to be heard. We often mistake our instruments for omniscience. We think that if the radio dishes are quiet, the cosmos must be too, but maybe we're listening in the wrong language. Maybe this visitor speaks in heat gradients, in particulate arrangements, in angular momentum shifts too subtle for our tools to isolate. Or maybe it's just a comet with timing so perfect, direction so improbable, silence so absolute that it's made us question whether we really know what a comet is anymore. And maybe that's the point. It arrived with no announcement. It burns without shouting. It passes through our solar system like a ghost that decided just once to shimmer in moonlight. And we were left with images that glow, jets that defy the sun, and data that hums with a question louder than any signal could ever be. Because if this is silence, what does a scream look like? There's still a natural explanation. Maybe. There's a rule in science we rarely say aloud, but we all obey. If something looks unnatural, try harder to prove it isn't. Because natural means we can eventually understand. And unnatural? That's where the rules go to die. So let's stay grounded for now. Let's try to explain what shouldn't be explainable. Let's try to save the laws of physics. Because if 3I Atlas is ejecting a jet directly toward the sun against all known sublimation thermodynamics, all angular momentum principles, all escape pressure vectors, then something else must be happening. Something natural. Something just misunderstood. We begin with the shape. Most comet models assume a lumpy, rotating ice rock body, riddled with vents. Those vents, holes or fractures are like nozzles. If they face away from the sun and heat up, gases sublimate and explode outward, creating thrust. That thrust, in turn, nudges the comet ever so slightly off its predicted path. We call that non-gravitational acceleration. The direction of those nudges? Predictable. The location of jets? Modelable. The cumulative effect? Mappable. Until now, the jet from 3I Atlas points toward the Sunday. It accelerates away from the Sunday, and that's the inverse of what should happen. So we ask, could the shape of the object combined with its spin and solar illumination cause a vent to behave this way? Possibly. Here is how the math might work. Imagine a deeply embedded CO2 vent, not on the comet's day side, but near the terminator, that boundary line between light and dark. Now imagine the comet spinning. If that spin brings the vent into a heated zone only briefly, just enough to warm CO2, but not enough to sublimate surface ice, then you might get a highly directed jet, a narrow stream, a flash of momentum. And depending on the vent's geometry, its angle, depth, and curve, the outflow could be redirected, not outward, not backward, but forward, toward the Sunday. Not by intention, but by accident of geometry. It's not unprecedented. CO2 is known to behave differently from water vapor. It sublimates at lower temperatures. It requires less energy to turn into a gas. It doesn't leave obvious OH trails, so it can escape detection unless you know where to look. This brings us back to the 18 cm OH line. MeerKAT detected it, faint, but real, indicating that somewhere water was involved. But it was secondary. The main actor may have been carbon dioxide. And CO2 is tricky. It can erupt through microfractures. It can rebound inside cavities. It can curl around surface features and mimic forward jets. And if the body of 3I Atlas has even slight asymmetry like a slope, a concave feature, or a rotational wobble, then thrust vectors could curve in strange directions. You wouldn't need alien engineering, just inconvenient physics. But that's a big if, because this theory, elegant though it is, has never been tested in this exact context. The thermal models don't match the acceleration. The outgassing simulations don't produce sustained jets, and the light curve doesn't confirm a spin consistent with that vent geometry. At best, we can say, it's not impossible. At worst, it's a patch, a temporary fix to preserve the idea that nature always has an answer. Some argue that a delayed CO2 burst could explain it, that 3I Atlas stored energy beneath a surface layer, and as it approached perihelion, a crust cracked open, releasing a superheated pulse. One vent, one rotation, one moment of perfect misalignment, just long enough to make a jet face the Sunday. But this raises questions. Why didn't we see a fragmentation? Why didn't we detect a thermal spike? Why does the jet seem sustained, not a one-off event? Some posit cold gas thrusting a mechanism observed in spacecraft engineering, where momentum is achieved not through heat, but through pressure release in confined environments. Could nature build a cold gas jet? Could subsurface pressure do what solar energy couldn't? Maybe. But there's no observational evidence for it on any other comet. No example where a natural body, without artificial chambers or materials, emitted a stable, directional gas flow into the direction of its solar source. So the theory remains possible, but unverified. Still, the scientific method demands we explore all natural explanations before we entertain the exotic. So we simulate, we run spin models, we test all plausible axes. We try convex bodies, concave ones, tumbling rotators, thermal lag, delayed sublimation, night-side heat retention. None of them fully recreates the trajectory, jet angle, and OH data together. Not yet, but this doesn't mean nature failed. It may just mean we're missing data. Comets are notoriously hard to model. They're irregular, non-uniform, highly reactive. What we see in a frame may be a mix of jet, tail, and reflection. What we think is a plume may be a stack artifact. What appears directional may be an illusion of geometry. So we tread carefully, because if we say this is unnatural too early, we stop looking for the natural patterns. And history warns us, nature is often stranger than we think. The Tunguska event, initially blamed on aliens, was likely a fragmenting meteoroid. Oumuamua, first labelled as artificial, may have had delayed hydrogen outgassing. Science wins when it waits. So we wait. We continue testing natural models, even the improbable ones. Because if one of them fits, no matter how awkwardly we preserve the beauty of physical law, still, something is haunting about this jet, not just because of where it points, but because of what it refuses to explain. The brightness, the symmetry, the persistence. It looks designed. And that's the danger. Because the moment we say that, it stops being science and starts being a myth. So we sit with both possibilities. The jet may be natural, it may be strange, CO2 dynamics. It may be a rotational coincidence. It may be a fractured vent at just the wrong place and the wrong time, and that might be enough. Or it might not. If it isn't natural, what is it? Something about 3I, Atlas, doesn't settle. Not in the models, not in the images, not in the language we've used to describe it. It moved like a comet until it didn't. It jetted like a comet until the jet faced the Sunday. It glowed like ice until the OH signal said otherwise. And so we've followed the logic. We've tested the known physics. We've mapped the potential natural explanations. We've talked about CO2 jets and spin-induced torque. We've invoked asymmetry, surface fractures, heat gradients, and mass loss. Each step, the goal has been to remain within reason, to remain anchored to the physics we understand. But what if we can't? What if that plume, sudden, directional, sunward, wasn't the product of chaos, but of control? Because here is the quiet truth. 3I, Atlas, has done something no comet is supposed to do, and it did so in silence, with precision, and without breaking itself apart. It changed its energy budget. It changed direction. It kept a stable light curve, and it stayed intact. We have one other object that did that. Its name was Oumuamua, and that's where Avi Loeb enters the story. Loeb, a tenured professor at Harvard, and the former chair of its astronomy department, didn't wait for institutional permission. After Oumuamua's strange trajectory, he suggested something radical, that the object could be artificial, not just in composition but in origin, not a rock flung by gravity, but a relic of intelligence, a solar sail, a light sheet, a probe. He was ridiculed, until some of his predictions started coming true. Oumuamua's lack of a coma, 3I, Atlas, did that too. Its non-gravitational acceleration without visible exhaust, 3I, Atlas, echoes the same anomaly. Is its stability across extreme thermal shifts, 3I, Atlas, passed perihelion without disintegrating, defying most thermal models that suggested it should have exploded. And now we see something new, a plume facing the Sunday. A jet was pointed in the wrong direction, an outburst that appears aligned with an axis rather than a random vent, a moment of energy expenditure that changed trajectory but not structure. This is not a claim, it is a question, and that question is made sharper by one detail: energy efficiency. If 3I, Atlas, is natural, it's one of the most efficient objects we've ever seen. A single, brief, outgassing event, possibly from one well-placed vent, was enough to change its orbit without triggering mass loss, rotation drift, or light curve disruption. That's unusual. If it's artificial, it's also efficient and deliberate, because energy control thrust vectoring requires design. Jets need directionality. No comet vents with precision, but a spacecraft might. So we look again at the plume. It wasn't diffuse. It was directional. It wasn't dim. It flared brightly, enough to register on stacked SOHO imagery, enough to create an anti-tail illusion. It wasn't repeated. It was isolated, and all of that suggests intention, or at least engineering. But what kind? Avi Loeb suggests possibilities rooted in our own understanding of low-thrust propulsion. He mentions light sails, thin, reflective surfaces that leverage solar radiation pressure to change velocity. He discusses thermal rebound effects, where layered materials emit heat directionally. More provocatively, he references outgassing control, not natural CO2, but engineered sublimation, a vent that releases material only when necessary. A form of interstellar braking or steering. These aren't ideas born of fantasy. They mirror the very systems we've considered for long-duration probes. The kind we'd send to another star. Now imagine something older. Imagine a probe built not by us but by another. Imagine it gliding through space, inert, for eons, until it nears a star, until sensors activate, until orientation shifts, and a small onboard system releases just enough material to nudge its course. Not to reach a destination, but to pass near observers, near Earth. We have no proof of that, but we do have an anomaly, a jet in the wrong direction, one that defies thermodynamics, sublimation models, rotational analysis, and energy limits. And we have a silence. No signal, no transmission, no ping, but maybe we're listening with the wrong tools, for the wrong signature. What if it doesn't broadcast on the radio? What if its message was the maneuver itself? What if the plume was not propulsion but punctuation? It didn't say hello. It said, look. And we did. We tracked it. We argued over it. We modeled it. We failed to explain it, and still it moved. So we circle back to a question older than astronomy. When we see something we can't explain, is it more rational to extend our models, or to ask if we're looking at something other than nature? Science demands caution. But curiosity is not a weakness, and so we don't make declarations. We open doors. 3I, Atlas, maybe a comet. An efficient, rare, asymmetric, tumbling comet. But if it isn't, then we are no longer just observing an object. We're observing a message. And maybe the most honest question is not what 3I, Atlas, is, but who sent it? Shadow isn't always what it seems. When we talk about seeing, we think of clarity. But the truth is, clarity depends on where you're standing, how the light hits, and what you expect to see. And with 3I, Atlas, everything about its light keeps challenging that expectation. Let's go back to the beginning. When NASA and other observatories began stacking images of this object, they weren't just capturing brightness. They were capturing change. Minute by minute, frame by frame, the light shifted, not in brightness alone but in orientation. The reflection wasn't constant. The object seemed to glimmer, then fade, then glow again, all with a rhythm that wasn't random. That rhythm is called a light curve. In astronomy, a light curve is how we measure an object's brightness over time. It's how we detect rotation, wobble, and axis tilt. With comets or asteroids, a steady periodic dip and rise tells us something is spinning. But 3I, Atlas, had a problem. The light curve was erratic. It didn't follow a clean sinusoidal wave. Some periods were symmetrical, others chaotic. The reflections came at odd intervals, and more than once, observers noted what appeared to be a jet, a concentrated outburst emerging from different angles over time. But no new jet had formed. So, what was happening? The answer lies in spin and shadow. 3I. Atlas is not a sphere. That much we know. Most cometary nuclei are irregular, often cigar-shaped, elongated, or even bilobed, like 67P, Churyumov, Gerasimenko. Shape matters because it determines how light bounces. An elongated object spinning on a tilted axis will reflect sunlight differently depending on its position relative to Earth. A jet, or even a bright surface patch, can look like it's changing direction when it's simply rotating in and out of view. But here is the twist. In late October 2025, the jet appeared to point directly toward the Sun, something no known comet does naturally. The plume was visible in the sunward direction, not trailing away as sublimation theory predicts. So astronomers asked, could this be a trick of light? Could the object's spin be lining up the reflection with such precision that we're seeing something that isn't there? To answer that, we need to consider axis orientation. If 3I, Atlas's spin axis, is pointed near Earth's line of sight, meaning we're looking almost directly along the pole, then features near the equator would seem to rotate around a central point. Think of a lighthouse beam rotating toward and away from you. But if the spin axis is tilted just enough, and if a vent or reflective patch lies off-center, then during certain intervals, that feature could appear to point directly at us, just as it appears to point at the Sunday. This effect is intensified by phase angle, the angle between the sun, the object, and the observer. When the phase angle is small, meaning the sun and Earth are nearly aligned, even small protrusions or jets can create exaggerated visual effects. A single bright spot can mimic motion, elongation, or even directionality. But there's a deeper problem. The periodicity in brightness wasn't clean. It wasn't just spin. It was asymmetry. Multiple light curve models have attempted to fit 3I. Atlas's data double-peaked, triple-peaked, chaotic rotation, but none fit perfectly. One plausible scenario is a precessing spin axis. That is, instead of spinning like a top, it's wobbling, changing the direction of its pole over time. This would create variable reflection patterns and alter the perceived direction of any fixed vent. That could explain why, over weeks, the apparent plume orientation shifted in a non-linear way, first sunward, then slightly off, then seemingly perpendicular to the expected vector. But still, the sunward jet defies symmetry. So what if it isn't a vent? What if it's a surface facet, an angled face, like a mirror that happens to reflect light during a specific alignment? In this model, there is no actual jet. The light we see doesn't matter, it's a reflection, a coincidence of geometry, not propulsion. The comet remains passive, the illusion is ours. And yet, that theory breaks under certain frames, especially those captured in long exposures. In image stacks from HiRISE and amateur observatories, the bright region near the sunward limb persists even when the object has rotated. If it were purely a reflection, the angle should change. But it doesn't, at least not consistently. This suggests two possibilities. First, the object is spin-locked. If 3I Atlas is in a state of rotational damping, it may have aligned its longest axis toward the sun due to thermal torques, a phenomenon known as the Yorp effect. Over time, solar radiation can cause irregular bodies to settle into stable spin states. In such configurations, a vent near the subsolar point, the spot receiving the most sunlight, could remain illuminated and active longer than usual. Second, the plume is real, but so narrow and collimated that it appears reflective. If the vent geometry channels gas through a tight nozzle, the plume may resemble a beam more than a spray, and if that beam is optically dense, sunlight could reflect off its particles, creating a signature indistinguishable from surface reflection. In this case, spin and shadow aren't deceiving us. They're collaborating with the physics to produce an unprecedented behavior. There's one more layer: shadow bias in image processing. Astrophotography relies on contrast, but in stacking dozens of exposures, subtle gradients can amplify artifacts. A faint jet aligned with background noise may appear brighter or darker depending on filter application. If the jet points sunward, its contrast may blend with the nucleus glow, making it look like an extension of the core. This reinforces the illusion. A jet becomes a glare becomes an axis. So how do we know what we're seeing? The answer: we don't. Not fully. We have light curves, we have phase angles, we have reflection models and rotation simulations, but each comes with error bars, big ones. And in those margins, mystery lives. That's why spin and shadow matter. They remind us that the sky doesn't lie, but it also doesn't explain. We interpret, we model, we guess, and sometimes we get it wrong. 3I Atlas may be rotating in just the right way to fool our eyes, or it may be teaching us that some comets don't rotate like we thought. That shadow doesn't always follow structure. That jet doesn't always mean motion. That silence doesn't mean stillness. In the end, we're left with a ghostly streak in the data, a line where no line should be. A plume that points not away from the fire, but directly into it. And a shadow that isn't just the absence of light, but the presence of mystery. Two angles, one illusion. infinite interpretations. There's something deeply deceptive about simplicity. A line drawn through space, an object drifting along it, a streak of light seen from Earth all appear clean, definitive. But in astronomy, the geometry of light isn't just misleading. Sometimes, it's outright wrong. When NASA released the high-resolution imaging stack of 3I, Atlas, it did what all good data does. It sparked arguments, heated ones. Some scientists saw a jet, some saw a dust trail. Others insisted the feature was noise, an illusion of perspective, light scattered, stacked, interpreted by software filters, not objective reality. But at the heart of it, they weren't arguing about the object. They were arguing about where the eye meets the orbit, the camera angle. In space, there is no such thing as a neutral view. Let's visualize it. Picture 3I, Atlas, a nucleus no wider than a small city block, tumbling through space along a hyperbolic arc. Earth is never still. The sun is blinding, and the dust, if dust is present, doesn't float neatly behind like hair in water. It's subject to pressure, angles, temperature gradients, light scattering, and phase geometry. That last term, phase geometry, is where things get strange. Phase angle, in cometary imaging, refers to the angle between the light source, usually the sun, the comet, and the observer, us, or a telescope. If you imagine a triangle formed by those 3 points, the phase angle is the angle at the apex of the triangle. At very small phase angles, when the Earth is nearly aligned with the incoming sunlight, you often see something called forward scattering. It makes the comet seem brighter, sometimes eerily so. At high phase angles, especially when you're looking back toward the sun from the dark side of the object, you can see backward scattering or even enhanced shadowing effects. These angles matter because light isn't neutral. Dust particles aren't mirrors. Depending on their size, shape, and orientation, they scatter light differently. Mie scattering, Rayleigh scattering, geometric shadowing, all of these play tricks on the sensor. What appears as a jet might simply be sunlight bouncing off a cone of microparticles at just the right angle to elongate the reflection along one axis. This is how antitails are born. Not from material flying the wrong direction, but from geometry that bends our interpretation. There's a reason many scientists weren't convinced by the early images of the sun-facing plume. The alignment was close to the orbital plane, meaning the camera, Earth, and the orbit of 3I, Atlas, formed almost a perfect plane. In that orientation, any dust emission near the nucleus that spreads along the orbital path looks like it's pointing toward the sun, even if it's not. It's the same illusion that makes train tracks look like they converge at the horizon, even though they never touch. The illusion isn't the problem. The belief is, we tend to trust our eyes, even when the data isn't visual in the traditional sense. A composite image built from filtered data, stacked over several exposures, filtered for noise, contrast enhanced, and corrected for glare, is still interpreted visually. The human brain will always search for continuity, pattern, and direction, and 3I, Atlas, gave us one. A thin, luminous structure seeming to point backward along its orbital path toward the Sunday. It looked like a jet. It felt like a contradiction, but for many professionals, the geometry raised red flags. Some researchers used modeling software to replicate the view from Earth at the moment the images were taken. When they did, they found something interesting. Almost any symmetrical dust emission, even one from a conventional back-facing vent, would appear to point sunward due to the combined orientation of orbital motion and observer perspective. This phenomenon isn't unique. It has a name: projection effect. In observational astronomy, especially when working with long-range images of comets and asteroids, projection effects often mislead early interpretations. What appears to be a dramatic jet might be a slow, diffuse emission viewed edge-on. What seems like a shadow can be just a lack of forward scattering. In 2010, a similar confusion occurred with comet Elenin, where a diffuse antitail appeared to precede the comet, a visual contradiction that made headlines. It wasn't a mystery, it was a result of our location, the comet's tilt, and timing. 3I, Atlas, is no different, except for one key difference: the emotional weight of being interstellar. We want this to be strange. When something comes from beyond the solar system, it carries with it the gravity of potential, of meaning. We look at the same data differently. We tolerate anomalies longer. We let mystery linger. So even when the phase geometry might explain the illusion, even when the orbital alignment matches similar cases we resist. We search for a deeper reason, a harder question, a truth that might slip past geometry and land somewhere else, somewhere hidden. And belief, especially belief built on partial data, has geometry of its own. It forms from angles we don't even see, a suggestion from an expert, a viral post, a line of code in image processing, a still frame from a long exposure. All of it shapes the picture. All of it shapes us. That's the strange thing about evidence in astronomy. It's both abundant and evasive. For every answer it provides, it opens a door to interpretation. A tale isn't always a tale. A shadow might be an echo. A jet might be a ghost of dust filtered through phase angles and wishful thinking. Yet in this ambiguity, there is also power. Because when we admit that our view is partial, when we embrace that we're looking through a lens built by orbit, software, and starlight, we gain humility. And humility sharpens the question. It invites collaboration. It slows us down. It teaches us to look again. That's the real legacy of the jet that wasn't. Not that it fooled us, but that forced us to ask, what am I really seeing? And more importantly, what am I not seeing? Because the eye isn't just a receptor, it's a narrator. And every narrator has a bias. The countdown has already begun. On December 19th, 2025, something rare will happen, not in theory, not in a lab, but in real time, under the open sky. At a distance of approximately 1.8 astronomical units from Earth, 3I Atlas will sweep past in a configuration that hasn't occurred before and may never occur again. This isn't just a date on a calendar, it's a moment in geometry. Unlike the perihelion moment in June, when 3I Atlas was closest to the Sun, the December flyby is special for a different reason. It's us, Earth, that will be in position, not to intercept it, not to be threatened by it, but to witness it at the exact angle where illumination, rotation, and trajectory converge into the clearest possible view of the object's true nature. Observers around the world, amateur and professional alike, are preparing, not for spectacle, but for clarity. And in astronomy, clarity is everything. Let's break it down. As of mid-November, 3I Atlas is moving outbound, leaving the inner solar system after its historic Sun approach. The OH-18 come line, the non-gravitational acceleration, the suspected jet facing sunward, all of that has already happened. But now comes a different kind of test. Can we see what's really there when the noise dies down? The December 19 window provides a unique geometry. From Earth's perspective, we'll be nearly orthogonal, at a roughly 90-degree phase angle to the Sun object axis. That means sunlight won't be blasting directly into our instruments, and we won't be seeing the object in backscatter or forward scatter extremes. Instead, we'll get something closer to side lighting, ideal for capturing surface contrast and volume definition, especially with stacked long-exposure imaging. It's the moment for truth. If 3I Atlas is still emitting material gas, dust, ions, well no. If the sunward plume was a projection artifact, we'll see whether the same pattern persists at this new angle. And if there are changes, shifts in spin, new outgassing vectors, fragmentation hints, they'll show up. But there's something else this geometry gives us. It's not just about what we see, it's about what we don't see. At 1.8 AU, solar illumination is still strong enough for activity, but not blinding. Thermal pressure drops, outgassing slows, and in that quiet, the surface features the contours, albedo differences, potential venting regions may emerge with higher fidelity. If there are structural anomalies, flat planes, unnatural reflectivity, persistent brightness, not explained by rotation, well, catch them here. Why? Because motion betrays structure. In December, 3I Atlas will no longer be accelerating the same way it did near the Sunday. Its non-gravitational trajectory components will be less dominant, allowing modelers to trace its motion with greater confidence. And if any deviation persists, any acceleration not justified by solar heating, then that anomaly can no longer hide behind thermal models. This is why the December flyby matters. It isn't the closest point, it isn't the brightest, but it's the most telling. Think of it like a silhouette. Under harsh lighting, details are flattened, but in angled light, edges define form, depth emerges. And that's exactly what the 90-degree phase angle offers, edge definition across a mystery. Now, about the observing conditions. Sky watchers in the southern hemisphere will have the best chance of capturing extended observations throughout the night. Depending on exact ephemeris updates, the object may be visible in longer exposure, CCD and CMOS setups with modest aperture, 0.3, 0.5 meters class, provided optimal tracking software is used. Professional observatories will coordinate multi-band photometry and spectroscopy, especially those with access to instruments like VLT, Keck, or Gemini South. But even backyard astronomers can contribute. Photometric light curve data, time-lapse imaging, or even comparing infrared frames can help create a more complete profile of the object's behavior post-perihelion. There's also increasing interest from the radio astronomy community. While the 0818cm signal peaked in June, there's potential for residual emission. Facilities like MeerKAT and the GMRT in India may attempt low-noise integrations during December. If any secondary emission lines appear particularly related to H2O, CO, or ionized fragments, they could help resolve questions around sustained activity far beyond the Sunday. But this geometry isn't just an observational opportunity. It's a philosophical one. We often think of seeing as passive. The object emits. We observe. But in truth, the universe only reveals what our angle allows. The comet doesn't change. Our vantage point does. And sometimes, that's all it takes to rewrite a story. In June, many believed they saw a jet pointing toward the Sunday. In July, some called it an artifact. In August, the debate deepened. But now, 6 months later, we get to see the object from a new position. Not metaphorically. Literally. We orbit the Sunday, it moves outbound, the triangle realigns, and with it, the illusion breaks. So what should we expect? No one knows. Perhaps it will be quiet, just a fading light across a CCD array. Perhaps the anti-tail will reappear, but in a different direction. Perhaps nothing will show, and silence will speak. But what's certain is this: the geometry cannot lie. Only we can. Because in astronomy, geometry is the final referee. It doesn't care about narratives. It doesn't bend to viral headlines. It doesn't argue on internet forums. It just is. And that's why we prepare. That's why the countdown matters. On the 19th of December 2025, the Earth, the Sun, and 3I, Atlas, will form a momentary triangle that allows us to ask, once again, with clarity, what are we really seeing? And perhaps more importantly, are we finally ready to look without projection? The answer won't come in words. It'll come in light. And we're almost there. We were one update away from missing it all. That's not drama. That's not hyperbole. That's how close it came, how narrow the gap between silence and discovery, between business as usual and the beginning of questions we were not prepared to ask. Because for all our instruments, our code, our cadence of observation, there's something we rarely admit aloud. Our systems only work if they're looking in the right place and expecting the right thing. But 3I, Atlas wasn't what we expected, and so we almost missed it. Let's go back. Not to the moment the jet was first seen, but to when it could have been. In the final weeks of July, just after the object passed closest to the Sun, there was a burst of uploads from HiRISE and Soho. Most of them were routine. Calibration frames, tracking shots. Some with minor noise issues were flagged and dismissed. The usual flow. Inside that stream was a frame stack that showed something unusual, a protrusion near the sunward side of the object, inconsistent with expected light behavior. But it didn't match any alert trigger. Why? Because it didn't flare. It didn't move fast. And crucially, it wasn't where a jet was supposed to be. So it was archived, not ignored, just passed over. Then came a community upload. A small Chilean observatory, using low-resolution parallax correction, released a video stacking 64 hours of exposures. They weren't hunting for anomalies. They were testing lens stability. But in the corner, again, was the sunward extrusion. This time, the team enhanced the contrast, not as part of a search for jets, but as a debugging tool. And that's when it caught someone's eye. At first, they assumed it was internal lens reflection. They tried filtering it out. But it persisted, frame after frame, shift after shift, and it held geometry against background drift. This is the lesson we almost missed. The data doesn't scream, it waits, and unless you're tuned to its silence, you miss what it's trying to say. For weeks, the evidence had been there. A slightly asymmetrical brightness profile, a consistent deviation in tail angle under solar calibration, a faint, persistent pixel plume sunward in over a dozen independent stacks. Yet none of it triggered a response, because all of it fell outside the known bounds of what should be. What's worse is this: the longer it stayed undetected, the more it risked being overwritten. Telescope time is precious. Datasets are archived, compressed, and deprioritized. Had this anomaly waited one more week, had the Chilean stack not gone public, it might have faded into storage, misfiled among terabytes of ordinary. One more software update, one more scrubbed folder, one more edge case artifact tossed out in QA. Gone. And that's not just a technical risk, that's a philosophical one. Because if the jet is real, if this object is emitting something sunward, defying expected dynamics, then this was our one chance to notice it when the angle was just right. Not too close, not too far, not obscured by flare. If we had missed it, we would have built the rest of the model on incomplete data, and every future conclusion trajectory, energy budget, survivability would be based on a distorted premise. It's happened before. In 1986, Vega 1 flew past Halley's comet and missed an early jet signature because it didn't fall within the predicted angle of observation. In 2015, a faint ion tail in Comet Lovejoy was dismissed for weeks until spectral layering revealed its persistence. In 2017, Oumuamua's non-gravitational acceleration wasn't noticed until long after it left the inner solar system. Each time, the data whispered first. We just weren't listening. And that's why this moment matters. Not because the jet proves something exotic, not because it rewrites physics, but because it reminds us how fragile perception is. This wasn't a failure of technology. It was a failure of framing. Our filters are tuned to detect brightness thresholds, shape anomalies, and motion vectors. But what if the real discovery lies just outside those parameters? What if it doesn't flare, it just leans? What if the clue isn't in what appears, but where it doesn't disappear? What if we only saw this because one team didn't clean the data too well? There's a deeper danger here. The illusion of certainty. We trust our observatories, our models, our layered simulations, and when the data conforms, we feel safe. But now and then, the sky offers something that doesn't fit, and instead of saying we don't know, we call it a glitch, a smear, a compression artifact, anything but what it might really be. New. This is how we miss things, not through blindness, but through overconfidence. So, what do we do now? We reprocess, we reframe, we go back to the July stacks and look again, this time without expecting symmetry, without assuming the jet must follow the tail, without insisting that comets behave. Because maybe this isn't a comet, or maybe it is, but not like the ones we've seen. Maybe it's older, stranger, from a place where heat behaves differently, where jets carve strange geometries, where ice doesn't mean quiet. Maybe the jet points toward the sun not in defiance, but in design. And maybe we were never meant to understand it the first time, but we're watching now, and the countdown has begun. Silence speaks louder than denial. It's easy to assume that if something extraordinary were real, NASA would say so, that if an interstellar object released a jet in the wrong direction, anyone would raise a hand and confirm the anomaly. But what if they don't? What if the truth isn't hidden behind lies, but behind press releases that say just enough without ever saying too much? Let's begin with what NASA has said. The Jet Propulsion Laboratory's official 3I Atlas tracker page still lists the object with its provisional name, orbital parameters, and standard solar proximity modeling. The trajectory chart was updated in early October, just after the MeerKAT OH line detection became public. But no mention of the plume, no headline, no alert, just updated numbers. The most direct acknowledgement came not through NASA's main page, but through a brief addendum on the HiRISE raw imagery portal. Unusual solar-facing illumination artifacts visible in process stack. Under evaluation, that's all. The phrase illumination artifacts is doing heavy lifting here. It suggests something visual, something not real, merely a byproduct of angle, stacking, or processing. It's a catch-all label, one that sounds scientific enough to avoid questions, but vague enough to avoid commitment. And that's the pattern. Not denial, not confirmation, just managed ambiguity. This isn't new. In 2017, after the detection of non-gravitational acceleration, in Oumuamua, NASA's response was minimal. The data came from multiple observatories. The modeling came from ESA and Harvard. NASA acknowledged the motion change but didn't offer a model. They cited unknown outgassing behavior, then shifted focus to future survey improvements. In 2021, when CNEOS data appeared to confirm the 2014 IM-1 interstellar impact near Papua New Guinea, the memo was classified for years before it was quietly approved. Again, not because NASA rejected it, but because they didn't prioritize releasing it. There's a difference between withholding data and not emphasizing it. The 3I Atlas case falls into the second category. If you read carefully, the clues are there. In a late October telebriefing about solar system dynamics, a NASA spokesperson was asked by a Reddit-compiled science journalist whether the 3I Atlas O detection confirmed active water outgassing. The reply was, "We're aware of radio reports suggesting molecular line activity near the object. We look forward to deeper analysis from the team and welcome more data as it becomes available." That's a non-answer, but it's also not a denial. It means we see what you see, but we're not putting our name on it yet. Which begs the question, why not? Part of the reason is institutional rigor. NASA, like any scientific body, follows a chain of evidence, peer review, and confirmation. No single image, no matter how stunning, overrides the process, especially when it comes to phenomena that bend expectations. Another part is risk management. If you call something a sunward jet, and it later turns out to be a processing illusion, you've not just made an error, you've made a public one. That's why internal language is conservative, and external language even more so. But there's a third reason, a deeper, quieter one. Sometimes, not confirming is the only way to avoid committing to a framework that may be obsolete. If 3I Atlas really is emitting in a direction contrary to all known jet dynamics, then the real question isn't what it's doing, but why our models didn't expect it. And admitting that requires more than a press release. Let's return to the HiRISE stack. Frames 1372A through 1384B show the anomaly most clearly. A faint protrusion at a sunward angle, stable across 6 hours. The internal flag was IRR, SUS, a label that means irregular, suspect, typically applied to cosmic ray noise, but occasionally to unmodeled structural emergence. This label doesn't mean invalid. It just means not explained. The fact that this flag wasn't escalated suggests a decision. Let it sit, observe, but don't amplify. Why? Because visibility creates pressure. Say too much, and you spark a viral storm. Say too little, and you risk being accused of hiding something. So the solution is, say just enough to remain blameless. That's the strategy. Of course, NASA isn't a monolith. Within the agency, there are debates. Some teams may want to go public. Others prefer to wait for JWST confirmation. Others are simply overtasked and underfunded, trying to process petabytes of data with a handful of staff and a swarm of AI filters. But here is what matters. No one inside NASA has said this is false. The anomaly remains visible. The OH detection remains public. The trajectory updates are ongoing, and in an age where data can be erased with a click, that silence is loud. Now contrast that with what they do talk about: new asteroids, DART missions, exoplanet transits, solar flares. Every day, NASA pushes out updates that match expectations, confirm models, and reinforce the narrative of a universe we understand. But when something appears that we don't understand, there's a pause. Not because it's unworthy, but because it's uncomfortable. 3I Atlas doesn't fit. It emits sunward. It twists its spin. It radiates water when no ice should survive. And it stays quiet on every high-energy frequency. That's not easy to explain, so NASA waits. But here's the shift. NASA isn't the only watcher anymore. The public has access to SOHO stacks, HiRISE repositories, MeerKAT data. Amateurs with AI-enhanced filters are catching anomalies faster than official teams. We live in an age of shared sky, and shared silence no longer protects authority. It fractures it. If NASA doesn't speak clearly, others will speak loudly. Some will shout alien, some will shout cover-up. Most will just ask, why isn't anyone explaining this? And they'll be right to ask. So what can NASA confirm? That 3I Atlas exists, that it came from interstellar space, that its motion is non-gravitational. That water outgassing is confirmed via the OH line. An anomalous plume appears in processed HiRISE frames. That's a lot. What they haven't confirmed: the plume's source, its composition, its directionality, whether it's natural, whether it's real-time, or an artifact. And that's where silence lives, in the space between detection and interpretation. So what happens next? December 19th. The object will pass close enough for Earth-based telescopes to attempt a synchronized stack. If the sunward plume appears again, especially from a different angle, NASA won't be able to remain neutral, not without consequence. Because this time, the silence will no longer speak louder than denial. It will be denial. And well, no, because we watched it first. And we're still watching. Every breakthrough starts with "that's impossible." It's almost a requirement. If an idea isn't first dismissed, laughed at, ignored, or flagged as an error, it rarely becomes the foundation of a revolution. And that's the quiet truth no one tells you about science. It grows, not by confirming what we know, but by colliding with what we don't. So, when an object like 3I, Atlas, emits a jet that seems to defy every model, maybe the real story isn't what we saw, but how we reacted. Because impossible is never the end of a question. It's the beginning of a better one. In 1962, philosopher of science Thomas Kuhn introduced a word that would forever alter our understanding of how knowledge evolves: paradigm. To Kuhn, a paradigm wasn't just a theory. It was the entire worldview in which that theory made sense. A system of assumptions, definitions, methods, so deeply embedded that we don't even see them until something breaks. Kuhn called it an anomaly, a result that doesn't fit, a behavior that refuses to conform, a glitch in the matrix of explanation. And when anomalies accumulate, when they can't be patched, excused, or ignored, something shifts. A paradigm shift. This isn't philosophy for philosophy's sake. It's the backbone of modern science. When Mercury's orbit precessed more than Newton's laws allowed, we didn't abandon physics. We found relativity. When photoelectric observations contradicted wave theory, we didn't dismiss the data. We built quantum mechanics. When the universe's expansion seemed to accelerate, we didn't delete the graphs. We discovered dark energy. Anomalies are friction, and friction generates heat. And heat is what powers transformation. So, if 3I, Atlas, points a jet toward the sun, if it stays intact when it shouldn't, if it emits water from inside a likely rocky shell, that's not a bug, that's a door. The problem is, doors are scary. They mean admitting we're not done, that we don't know everything, that our models, beautiful, trusted, and often accurate, might be blind to something larger. And that's hard for any discipline. Because science thrives on control. It's built on predictability, the language of equations, the comfort of constants. We test things so they stay tested. But nature doesn't care what's easy to model. It doesn't care about institutional caution or PR strategies. It doesn't wait for budgets, grants, or telescope time. It simply behaves. And when it behaves in ways that seem impossible, it's not wrong, we are. The jet from 3I, Atlas, isn't just a technical puzzle. It's an invitation to revisit assumptions. That sublimation must always push away from the Sunday. That light curves always indicate spin, not shadow. That water must mean ice, and ice must mean comet. That a quiet signal means nothing's there. Each of these is an assumption embedded in our paradigm, and each of them may be incomplete. But we only notice that incompleteness when something misbehaves. When a visitor from interstellar space sends a message not in words, but in physics. A message that says, "Your models aren't broken, they're just too small." It's easy to forget this, because science, like all human endeavors, becomes ritual. We repeat experiments, we cite papers, we validate the known. But breakthroughs never come from the known. They come from ruptures. Someone sees something they shouldn't, a pattern in the noise, a light in the wrong place, a direction that contradicts the rules, and then, if they're brave, they speak up. And that's when the system pushes back. With skepticism, with laughter, with silence. Silence is what 3I, Atlas, has met so far. Its behavior hasn't been explained. Its signal hasn't been denied. Its image hasn't been removed. But no one wants to say what it means. Because saying what it means might unravel other things. If this jet is real, what else might be possible? If OH lines can appear without a coma, what defines activity? If spin and jet orientation can decouple, what else can? If CO2 jets can hide behind thermal shadows, how many have we missed? Each question isn't just about this object. It's about all objects. It's about re-auditing the cosmos. And that's the point. There's a reason revolutions feel like betrayal. They challenge the people who built the current model. They ask scientists to question their mentors. They ask engineers to unlearn frameworks. They ask institutions to tolerate uncertainty. But without that tolerance, we go blind. We become custodians of dogma instead of explorers of truth. And the universe deserves better. 3i, Atlas deserves better. Because even if it turns out to be natural, just a fluke of geometry and timing, it's still telling us something we didn't know, something we couldn't simulate, something that shouldn't have happened but did. And that gap is where science grows. Kuhn warned us that revolutions don't look like fireworks. They look like resistance, like confusion, like denial, until suddenly, one day, we look back and say, of course, that's how it works. How did we ever think otherwise? Maybe 3i Atlas is part of that shift. Maybe its sunward jet will one day be a textbook diagram, a case study in model revision, an example of what happens when the sky behaves differently. But to get there, we need to pass through the discomfort, through the phase where people say, that's impossible, and ask instead, what if it's not? Because the phrase, that's impossible, isn't a warning, it's a flag. It marks the edge of a map, a place where dragons were drawn and science now begins. We used to think the Earth was flat, those diseases were curses, that space was still, that comets obey the Sunday. We were wrong, and being wrong wasn't the end. It was the first step toward being more right. 3i, Atlas is that step. Not because we understand it, but because we don't, and because the physics of the impossible is just physics we haven't met yet. What if the jet isn't the anomaly we are? It's an unsettling question, not because it implies we're wrong, but because it implies we may always be wrong in ways we can't fully detect. The more precisely we look at something, the more likely we are to change it or ourselves. This is the paradox of observation. And in the story of 3i Atlas, it isn't just an interesting philosophical tangent. It's central to the mystery. When we point our telescopes at the sky, we believe we are passive witnesses, eyes without influence, instruments of record. But that's not how perception works. What we see is never just light. It's light filtered through assumption, timing, angle, and above all, expectation. A jet pointing toward the sun violates our expectations, so we question the image, we question the angle, we question the optics, we question the data, but rarely do we question the frame of perception itself. The act of seeing is not neutral. Physicists have known this for over a century. In quantum mechanics, the observer effect is not metaphorical, it's literal. The very act of measuring a system can alter its state. Light behaves as a particle or a wave, depending on whether you look. But this isn't just a quantum quirk, it's a principle of awareness. In cosmology, observation is interpretation, and interpretation carries bias, sometimes subtle, sometimes profound. Every filter setting, every exposure time, every stacking algorithm reflects a choice. Not always a wrong choice, but always a framing choice. Take the HiRISE image that reignited the 3i Atlas debate. At first glance, it appears to show a jet pointing sunward, completely counter to our understanding of outgassing physics. But how was the image built? What time was it captured? What was the relative angle between the sun, the camera, and the object? What assumptions went into the noise reduction? What biases live in our eyes when we see what we expect a tail going away from the sun? It may not be the jet that misbehaves. It may be us struggling to interpret a behavior that sits outside our default categories. This isn't to say the jet is imaginary. Far from it. Multiple images confirm the structure, but even confirmation carries interpretation. We assume a jet is gas or dust. We assume it originates from a surface vent. We assume the sun pushes it away via heat and radiation pressure. But those assumptions come from thousands of observations of other comets. This isn't another comet. This is a visitor from interstellar space. A traveler forged under another star, shaped by unknown forces, unbound by the thermal history we use as a baseline. So when it behaves in ways we haven't seen, is that an anomaly? Or is that what anomaly always looks like before we understand it? There's another layer here, one we don't talk about often in science: emotional bias. It's not just about models, it's about meaning. We want the universe to behave. We want order. We want comets to be comets, stars to be stars, and jets to follow thermodynamic rules. Because when they don't, it unsettles more than data. It unsettles us. It makes us question not just our instruments, but our confidence. And confidence is hard-won in astronomy. Each mission takes decades. Each discovery passes through layers of verification. No one wants to leap toward the mysterious without guardrails. But too much caution becomes its own bias. We look with eyes trained by confirmation, not contradiction. And this is why the 3I Atlas story matters beyond astrophysics. It's a mirror. It shows how we react to the unexpected. Do we dismiss it? Do we delay it? Do we discredit those who report it? Do we reprocess the data until the anomaly vanishes? Or do we sit with the discomfort? Do we let the anomaly remain visible, unassimilated, provocative, until we have tools big enough to hold it? That's not just a question for astronomers, it's a question for all of us. Think of how many times in history the anomaly was real. The retrograde motion of Mars, the shifting orbit of Mercury, the background radiation of the cosmos. Each began as an observational nuisance, a bad result, a data point outside the curve, and in each case, the breakthrough only came when someone looked again not at the data, but at the way we looked. 3I Atlas is asking us to do the same, not just to revise models, but to revise perception itself. There's a humility here, a gentleness, a kind of reflective pause in the rush to explain. What if, just what if, the cosmos is not built to match our minds? What if our minds must stretch slowly, painfully, and beautifully to meet the cosmos? And what if the jet is not breaking the rules, but reminding us that we wrote them too early? None of this means we discard science. It means we strengthen it by honoring its deepest core, curiosity. Curiosity is not about certainty. It's about attentive doubt, about asking again, looking again, about not rushing to reduce the strange into the known. 3I Atlas resists reduction. It's quiet, it's distant, it's steady. But in its path, it's left a streak of cognitive dissonance, one we must decide what to do with. Do we flatten it or follow it? This is the observer's paradox. We think we are watching the comet, but maybe it is watching us. Watching how we respond, watching how we explain, watching whether we still possess the capacity for wonder, not just in space, but in the way we think. And if it is a mirror, then what it reflects is our next step. A chance to observe observation itself, to ask, what are we assuming? What are we ignoring? What are we afraid to admit we don't know? Because sometimes the anomaly is real, and sometimes the anomaly is us. It's still here, still active, still unknown. That alone should stop us. In a cosmos where most comets fragment, fade, or simply vanish from record, 3I Atlas continues to defy the script, and we are still watching. We expected an ending. When 3I Atlas rounded the sun, it should have been the climax. The heat, the pressure, the energy budget, all of it pointed to fragmentation, sublimation, disruption. And yet, it endured. Even now, as it recedes toward 1.8 AU, it emits, it jets, it holds together. Not only has it survived, it remains visibly active, visibly alive in the language of astronomy. Let that register. We are observing an interstellar object, still jetting, still whole. This is not how most cometary bodies behave, especially those with eccentric or hyperbolic trajectories, moving at such velocities, exposed to such thermal gradients. The closest analogues, Oumuamua and 2I, Borisov, each told different stories. Oumuamua, silent, spin-locked, unilluminating. Borisov, dust-heavy, more familiar. But 3I, Atlas, it's the bridge between silence and motion. It offers structure yet mystery, activity yet no explosion. This paradox is observable, verifiable, and undeniable. Let's walk through what we now know. 1. The OH line stayed consistent. MeerKAT and follow-up arrays confirm the presence of the 18 cm OH radio emission, a byproduct of photodissociation from H2O. This is not noise, it is chemistry, it is water. Outgassing behavior suggests sustained sublimation from ice-bearing material at distances and temperatures where such activity should taper off. And yet, it did not. In fact, the persistence of the OH line across observational windows indicates not a dying comet, but a controlled burn. Either the venting is modulated, or the internal reservoir is structured in a way we do not yet understand. 2. No sign of fragmentation. HiRISE imagery, SOHO tracking, and other deep-field composites show no signs of nucleus breakup. The structure remains centralized. Brightness has not dropped precipitously. No debris field follows its path. This is key. Cometary bodies that survive perihelion usually display shedding of smaller fragments, increasing tail length due to unbound particles, irregular brightness, fluctuations from partial collapse. But 3I, Atlas, has shown none of this. Instead, it maintains a coherent signal. A body that stays whole through this kind of thermal encounter is rare. A body that stays whole and still jets is rarer. 3. Directional jet persistence. That sunward jet, the anomaly that triggered this documentary, is still present in multiple stacked images. Even weeks after perihelion, with solar radiation pressures reduced and the angle of incidence shifted, the structure persists. Some models suggest that jet direction should now swing outward due to illumination changes, but it hasn't. Not fully. There's still a strong vector that aligns not away from the sun, but toward the previous geometry, which begs the question, is this inertia, or is the vent itself locked in a spin mode that reorients to compensate? Either way, the jet continues. It is not a flare. It is not a noise artifact. It is a feature. 4. A heat budget that doesn't add up. By all estimations, the thermal energy absorbed by 3I, Atlas, during its closest solar pass, should have vaporized much of its volatiles, if not collapsed the structural integrity of the body. But current surface temperatures, estimated by reflection spectroscopy, suggest minimal energy loss through traditional sublimation, which means one of two things. The surface is shielding internal ice in a way we do not expect, or the jet's energy comes from a different kind of release mechanism altogether. Could there be internal reservoirs exposed only via fracture channels? Could insulation layers delay thermal transmission? Or more strangely, could outgassing be triggered by something other than the sun? 5. Silence around the signal. Despite the clear OH detection and multiple optical confirmations of jet activity, there has been little formal consolidation of the data by major space agencies. No strong press release, no working group announcement, no coordinated campaign for December follow-up, just scattered tracking, quiet commentary, and vague references to anomalous directionality, which brings us to a different kind of observation. What happens when a phenomenon doesn't fit? Do we amplify? Do we silence? Or do we wait? Because 3I, Atlas, continues to provide input, and we seem hesitant to engage. 6. The December opportunity. On December 19th, at 1.8 AU, Earth will hold an ideal observational alignment with 3I, Atlas outbound path. This geometry matters. Well, see, sunlight refracted through the jet structure at a sharper angle, potential nucleus rotation at longer dwell times, increased signal-to-noise in OH line measurements due to reduced solar interference. This moment could confirm whether the jet is a persistent exhaust vent, a visual artifact, a misinterpreted reflection, or something else entirely. But that window is brief, and the object is fast. If we hesitate, we lose it. 7. The emotional undercurrent. There's awe here. Not the awe of vastness, or beauty, or cosmic scale. This is the quieter awe, the kind that arrives when something simply persists longer than it should. A visitor who keeps emitting, keeps gliding, keeps evading our simple boxes. It hasn't exploded. It hasn't been silenced. It just continues. And in that continuation, it teaches. We don't need answers today, but we do need to stay awake, Because 3I Atlas hasn't ended its story, and we haven't asked our final question. It's still here, still jetting, still whole, still waiting for us to listen with better tools, clearer minds, and eyes no longer shocked by what doesn't make sense, but drawn to it. Because that's where the real science lives. Some stories don't explain, they transform, and this was one of them. From the beginning, this wasn't about danger. It wasn't about aliens. It wasn't even about comets. Not really. It was about a moment, a fragile, quiet moment, when the sky gave us something strange, and we had to decide what to do with it. It wasn't bright. It wasn't loud. But it was there. A jet, pointing toward the Sunday, in defiance of physics, in defiance of everything we thought we knew about the way comets behave. Most people never noticed. Most agencies said nothing. Most theories stayed silent. And yet, it moved. We watched it emerge from noise. We tracked it with cameras not meant for such detail. We heard a signal that shouldn't exist. We saw light scatter in directions that couldn't be explained. And we witnessed something holding itself together far longer than it should have. But maybe the real mystery wasn't the jet. Maybe the real anomaly wasn't out there. Maybe it was here, with us. Because the question this object asked wasn't, "What am I?" It was, "What do you choose to see?" For every comet, there's a formula, a model, a set of assumptions about ice and rock and heat and dust. But for 3I Atlas, those models fractured. The anti-tail pointed the wrong way. The OH line appeared earlier than expected. No visible coma, yet clear non-gravitational acceleration. No thermal destruction, even at perihelion. No debris trail, even after the closest pass. And through it all, still whole, still jetting, still silent. It didn't explode. It didn't fade. It lingered, almost like it wanted to be seen. What does it mean to witness? To truly watch, not with judgment, not with conclusions, but with presence. It means opening yourself to what is, even when what is doesn't fit. It means being willing to look at something that breaks your model and say, "This happened. I don't know why, but I saw it." It means understanding that sometimes light doesn't lie, and silence doesn't mean absence, and memory, when shared, becomes evidence. There's a quiet revolution happening in science right now. A shift from certainty to curiosity, from control to compassion, from answers to questions. This object, whatever it is, wherever it came from, wasn't here to give us closure. It was here to test our humility, to ask if we're ready to accept a sky that doesn't always make sense, to accept that not everything needs to be solved to be meaningful, to remember that observation itself is an act of reverence. It didn't need to shout. It just needed to be real. In 1908, we missed Tunguska. In 2017, we argued over Oumuamua. In 2023, we saw 3I Atlas arrive with a jet that shouldn't be. How many more visitors will come and go before we learn that seeing is not enough? We have to pay attention, not just to the data, but to the silence between the data, to the patterns that form, then dissolve, to the memories we carry not just as scientists, but as a species learning how to look. Some people need it to be natural, some need it to be artificial, some need it to be nothing at all. But maybe the most important thing was present. It was there. And because it was there, we got to decide what kind of observers we are. Are we the kind who only trust what we expect? Or are we the kind who allow the universe to surprise us? Well, keep running models. Well, keep arguing over spin axis and vent geometry. Well, keep stacking frames and calibrating detectors and waiting for the next anomaly. But underneath it all, well, remember this. The strange light, the silent jet, the December approach, the lack of an explanation, the tension of not knowing, and the peace of letting that be okay. Because some truths aren't delivered. They're revealed slowly in reflection. And that's what 3I Atlas offered us. Not a headline, not a verdict, a mirror. So what now? Now we wait. We watch the next flyby. We recheck the light curves. We debate the origins. But we also remember that this moment, this anomaly, was not about proving anything. It was about remembering how to wonder, how to look up, how to say, "I don't know," without fear. Because in the end, we are not just scientists, we are witnesses. And witnessing carries weight. It means being present when no one else is. It means being willing to stand in front of something that doesn't make sense and stay. Not run, not reduce, just stay and listen to the silence, to the light, to the sky itself. So maybe the jet didn't change the world. Maybe it didn't rewrite physics. But it rewrote something in us. It reminded us what it means to see, to pay attention, to let mystery live without rushing to kill it with theory. It reminded us that some stories don't end with answers. They end with resonance. And sometimes that's more powerful than truth. We saw it. We stayed with it. We chose to see. And that, maybe more than anything, is what made it real.